Okay, guys, let's get started. I sent the two mechanisms out. Guys, we've already taken up these answer sheets. Okay? We did that 3 minutes ago, too. Okay, we had two mechanisms. I sent those out to you. The ring expansion here, contraction, 7 to 6, contraction. I also sent you mechanism for the THC mechanism. Please look at those if you have not. Please be asking questions. Let's begin here with the cationic polymerization. Okay, our first look at a polymerization reaction. You take this simple alkene, what is that, 1 propene? 1 propene, does that look right? Actually, you don't need the 1 because there's no such thing as 2 propene. So that's just propene. Treated with an H plus catalyst, we can get a polymer here. And if you polymerize propene, which is also called propylene, what do you get? You get polypropylene. Anybody got a water bottle? You probably have a polypropylene water bottle. Polymer is very important. Let's see how we can get to this polymer. We also need to know how to show polymers. The polymer may be shown just that. That's going to be all you'll see. What's in parentheses is this CH2 carbon methyl. And that's just repeated a gazillion times. What N is some type of huge number. Repeat, repeat, repeat. So we begin with a monomer, propene or propylene, so we can polymerize it to a polymer with multiple repeating units. We need to be able to show that in that type of style. Mechanism for this. Pretty straightforward. We have an alkene, we have H plus catalyst. That's the only reaction we've really seen thus far to begin. Where are we going to leave cation, left or right? H plus. The cation on the left, so we pull away here. Boom, boom, boom. We get this cation. Secondary, correct? Cation there would have been primary. No, that's good. Okay, what can happen next? Okay, if we were using something like HBr, Br minus could add here and we could get an alkyl bromide. If we had water could add here, we could end up with an alcohol after we lose the H plus. We'll talk more about the conditions here. But what needs to add here to get polymer? Polymer means it reacts with itself over and over and over and over. Reacting with itself. Another one needs to react here. Well, think about it. We have an alkene. We can bring in another one of these. Can an alkene react with a plus? Yes, H plus. And above, we saw it react with a C plus when we did an internal reaction. Intermolecular or intramolecular. Well, here we're just going to have another alkene react with this plus. Okay, we got an alkene reacting. Where are we going to leave cation, left or right? On the right. So we pull away from the right carbon, we go attack here. What does that give? Well, here you got to just keep track of everything. This is sort of going to be the beginning H that we added. I've got it drawn in right there. That's the beginning H that we added. Okay? And we can even call this maybe 1, 2, 3. And this here, maybe we could call, no, what quite number yet? Let me draw over here and maybe number it. What does this give? Boom, 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 H. Now something's bonded to this here. We have a carbon. I got a boom, boom. A 3-carbon unit and a 3-carbon unit. The result should be a 6-carbon unit, right? If we label this, I'm going to see if this works out, A, B, and C, it may get a little bit confusing. Which carbon is it bonding to 2? You got to see this. Which carbon is bonding to 2? That should be easy.
Isn't it B?
C. Yes, C. Here's the pi bond. It breaks away from B and hinges over and bonds to this carbon. C is now bonded to this carbon because it broke away from B. C is bonded to 2. Okay? If we number this 1, 2, 3, this is going to be C, B, A. Which bond did we just make with that arrow movement? The bond between C and 2. What should be on carbon B? What do we need to show?
Positive.
A carbocation, right? That used to be double bond, but the electrons broke away from B and went bonded to 2. Even that's a carbocation. We'll eventually clean this up. We got a carbocation. What can attack this carbocation? Another one. Another starting material. Another molecule of the monomer. Where do we leave cation? Left or right? Right, correct. These electrons pull away from here and attack here. I don't know what to number these. If that's 1, 2, 3, maybe we can call this 4, 5, and 6. What bond is being made here between carbon 4 and B? We can keep this the same way. H, boom, 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 boom. Now we have a new bond, and this is carbon, what, 4? And that's bonded to 5 and 6. We made that bond. Where's the carbocation now? Because if a plus reacts with a neutral, we should have a plus. Yes, 5, carbocation, right? That used to be the alkene. Electrons came over here and bonded, leaving 5 without a bond. Okay, what can attack that carbocation?
Another one.
How many times do we need to do it?
As many as you need to.
A gazillion. That's how you get to the polymer. Okay, what are we generating here? If you look at it, it's a repeating unit. We started with an H. After the H, it actually then starts repeating. Then we have a CH2 carbon methyl. CH2 carbon methyl. CH2 carbon methyl. And if we keep going, it'll be a gazillion CH2 carbon methyl. So how can we show that without just drawing a molecule 10 miles long? We can show it, H. After the H, what do I have? CH2 carbon methyl. So I got a CH2, which is going to be just like that. That's a CH2, right? Carbon methyl. But then I just kind of keep going, and it's going to repeat. And so I can kind of say, boom, boom. It just repeats. CH2 carbon methyl. That's going to be a CH2 if we drew it carbon methyl. Do it like this and just say N, some huge number. And right there is your product. That's how it's typically shown, your polymer. I showed it above, I just showed a few more of the repeating units. Typically you won't see, you'll just see one repeating unit with a type of N, meaning number. You got to keep track of how you're putting this together, right? Numbers and letters, I hope that sort of makes sense. We can see, so right here, carbon 4 is bonding to B, correct? That was B. I highlight the bond. I tell you I like to highlight the bond so we see it. It's obvious to see. And then you're ready for, it just keeps on reacting. Boom, boom, boom. Now, because this polymerization reaction began with a cation, H plus is a cation, right? The cation was like the initial reactant of reacting the monomer with a cation. It's called a cationic polymerization, initiated by a cation. If the alkene had been polymerized by reacting with an anion, it would have been called a anionic polymerization. If it had reacted with some type of radical, which we haven't seen radicals yet, that would be a radical polymerization. So this is a way to make polypropylene. That's polypropylene over there. Huge molecule. Questions?
Normally when you're doing stick structure, any carbon you assume has like all the hydrogens on it. But since, I understand that it only has 2 hydrogens on it, but how are we just assuming that you know that it only has that one extra hydrogen opposed to the other 2 hydrogens on it? Does that make sense?
Well, if there was only one there, then it would have to have a charge.
Okay, cool. That's how.
And so there's no charge. So we assumed that, I told you appropriate charge. I can't hide charges from you. If I'm hiding charges from you, then you're going to get the structure wrong. That's my fault. Assuming it's neutral as shown, then it has to be 2 H's there because one of the H's, that's actually a CH3, but it's, in terms of repeating unit, it's CH2 because the next one is going to be CH2. So this is outside the repeating unit.
Okay.
That first H was what initiated everything. Okay. All right, we're ready to move. Outline. We have outline. We just finished up use of appropriate catalysts. We can look back at that. What type of H plus source would you use? You just said H plus, that's very generic. What type of acid would you use? If you went to the stock room and you wanted some acid of this, you would tell the stock room attendant you want some what? If you say H plus, they're going to look at you like, I've got 100 varieties. It's like you go to the ice cream, you say, give me some ice cream, they're going to say, what kind do you want? What kind do you want?
A strong acid?
HBr? No, if you get HBr, Br minus is going to attack the cation. You don't want anything to attack the cation other than this attacking the cation.
So you want a weak acid?
No, you need a strong acid because alkenes only react with strong acids. H plus catalyst implies strong acid.
Sulfuric acid?
Sulfuric acid is better because we know the sulfate or the bisulfate anion will not attack cations. We said that 2 days ago. So yes, that would be a good choice. One of the potential problems is sulfuric acid is aqueous, and so you're going to have water there as well. Can water attack a cation? See, but it's better than HBr. What you really want is a strong acid that doesn't have a good nucleophile as the anion, and also that it's dry. And the only one that we've seen that's both that is HF. So HF is theoretically the better choice for doing this. Then you won't have anything competing with your cation, and this will be the only thing that can attack the cation. So you'll limit side products. Okay, we look up here at our outline. We've done all the reactions above, up here. And if you think about it, all the reactions we looked at so far involve reacting with H plus as the electrophile, as the initial electrophile, H plus. They've all been the same in that regard. They only varied by what nucleophile we used. And then we did some internal reactions. We did some second steps that varied. Polymerization. Okay. We're now moving down below. A lot more reactions, yeah. These are going to involve reacting with other initial electrophiles. These also will not involve a carbocation intermediate. One good thing about that is because they don't involve a carbocation, they're not going to be prone to rearranging. You only get rearrangements when you have carbocation. Typically, no other time. Especially not for us at the introductory level. Okay, so there's some information there at the heading. The first reaction we're going to look at is there, X2, which is halogen 2, like chlorine. Instead of HCl, well, HCl, we're going to do ClCl. Okay? Well, Br. This is your elemental halogens, X2. Chlorine, bromine. That's the first reaction, and it gives a trans dihalide. We're going to have more stereochemistry down here. We'll get into it. Then we'll move around, and we're going to come this way, and this will be the last one we'll look at. By the way, I do have a handout. We'll break it, cut it in half here. This is a nice little puzzle. Alkene reactions. Additions to alkenes. Alkene addition reactions. Lots of reactions, and this is for your practice. Every reaction possible products are shown on the next page. You choose your product. Each product has a letter associated with it. And between the number of the reaction and the letter of the product, you're able to fill in the answer to the riddle. The riddle is, how is the alkene able to learn all of its electrophilic reactions? The answer is because, and it gives you your answer. Basically, it's practice, okay? This was not made out by me. You can read the intro. This is the type of questions that organic students around the country are doing this fall, this week, or whatever. Okay? So, some practice and a little riddle. We'll see what came up with their answer to the riddle a little bit later. I will state here, has anybody got it yet? If not, who's got extras? Anybody need one? There are a couple of reactions we will not be covering here. I don't cover an organic 1, and thus I've already given you the answer. Those, I cover an organic 2. Okay, got the yellow sheet, and we're moving ahead. In terms of our outline, we're now down to B. Oh, we got a different category. Elections without carbocation intermediate. Yes? E plus is not H plus. E plus being a generic way to show electrophile. Number 1, anti or transition of halogen. And that's where we're at here. Actually, we're on the previous side, though. Okay. Now, all these reactions at the bottom, we got to look for the similarities in them. And what we show for the first one, we are looking for the similarities. We're going to recognize that, and then when we move ahead, we'll see the same type of thing. So we really need to understand the first reaction and the important concepts that are there. Okay, anti or transition of X2. This is typically going to either be chlorine or bromine. Okay? We'll say why at the bottom. Why only these two? These are the main two. Take an alkene, chlorine. First off, does chlorine have any polarity? Is it a polar molecule? Because HCl, remember, has polarity, right? And the H is what? Partial plus. You can even show it ionized, and we know that it readily ionizes and either creates this. So either one, you have something the alkene can attack. But what about chlorine, Cl2? Is it polar?
No.
Well, that should be kind of your answer. Problem is, chlorine and bromine, these guys are schizophrenic. Okay? And they're easily polarizable. How do you polarize something? Well, mechanical action will lead to polarization. You ever do that in physics? Boom, 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 then hold the balloon on the wall, it sticks? Because you have polarized it by induction. There's lots of ways things can become polarized even though they're not formally polar. But when you hear something that's bromine or is easily polarizable, what does that mean? It means it's easily polarizable. Okay? You got to kind of know that. So it's schizophrenic, and so if I show it like this, you got, instead of saying where did that come from, you got to understand that it's easily polarizable. And it can get to that state not on average, but at a certain time. Okay? You can read more about the idea of being highly polarizable. But because of that, it's schizophrenic. It gets into this situation here. One chlorine gets an attitude and says, even though we're not supposed to do this, I got an attitude, I'm pulling anyway, and I'm going to leave you partial plus. All right, enough of that. So we get some reactivity because of that. These electrons start being liking partial positives. And we do our same old reaction here. These electrons, and we kick this off. Note, we never show their halogens as ionic. It's okay to show this ionic, but not your halogens. We need to leave them covalent. And we attack and kick one off. We did that once or twice with the covalent HCl. So these electrons attack chlorine. These electrons move over there. What do we get? We get this structure. Where are we going to leave cation, left or right? Does that one ever change? On the left. So these electrons break away from that carbon and go attack the chlorine. This one gets kicked off. What does that give? We get this bond, because this carbon bonds here, and we leave this as a cation. First off, let's point out what we get from this reaction. In terms of what we get, it's one of the simplest reactions in organic chemistry. You end up with one halogen on each carbon of your alkene. One chlorine here, one chlorine here. One chlorine here, one chlorine here. So we say that we're adding the halogen across the pi bond. Do you have to worry about where the chlorine goes? Because if it was HCl, we would put the H would be where? H would be here and the chlorine would be here, as opposed to opposite. Do we have to even worry about that with this? No, if I put this chlorine here and that chlorine there, it would be the same exact result, right? So there's actually no regiochemistry in this reaction. You don't even have to think about that. Chlorine on each carbon. How do we get there? Well, right here, we bonded to one chlorine. Very similar to our previous mechanisms. How can we get the other chlorine there? Well, we could have the other chloride. Where did that come from? Right here. That arrow's got to mean something to you. These electrons move on to chlorine, they break away. Chlorine would form lone pairs. That's where that came from. This is a minus. These electrons could then add to the plus, and that would give you that product. Yes? The problem is, that's not the mechanism. That's not the mechanism. How do we know it's not the mechanism? We'll talk about that a little bit more later. For now, though, think about this. Which electrons can attack this plus faster? Because we have two lone pairs here. These electrons are actually going to attack faster than this. Because this chlorine is not bonded to the system. It can actually be way away. This is right next door, and this is faster. Okay? This is an internal attack. An intramolecular attack. By the chlorine that we added. This is the mechanism. This is called back bonding. I call it back bonding. Books may not call it that. It's faster. What does that lead to? If this chlorine attacks, we get this structure. This is a strange looking three-membered ring with a chlorine. It's called a chloronium ion because it is an ion. The chlorine is now positive. You can do a charge, it's positive. Chloronium ion. And it's at this point that the other chlorine comes in. Not here, but at this point. This chlorine or chloride comes in, still attacks this carbon, the same carbon that it would have been if it attacked here. But it attacks the chloronium ion. It comes in here and attacks this carbon and kicks off this chlorine. And this arrow movement gives you your final product. So the chloride does not attack the carbocation, but it attacks the chloronium. Now, this is attacking a carbon and kicking off a leaving group. Why would it attack that carbon? We know why this chloride would attack this, because it's a plus. Minus attacking plus. But why would this attack here? Well, it's not a formal plus, but it's got a lot of plus. We've got a dipole here. This chlorine is very electronegative. It's pulling. There's lots of partial plus here. And this is one of our standard mechanisms. Where have we seen this before? You've all looked at this, right? And learned that it's hugely important. There's two ways nucleophiles can attack atoms. We can attack a positive charge. By the way, when we attack a positive charge, what type of stereochemical outcome do we have? You get both, right? Remember last time we showed the positive charge and we had attacked it from both sides? So that's all there, right? All right, all this discussion is there. You've all mastered that or have been asking questions about it, right? There's a second way. We can attack a carbon and kick off what's called a leaving group. It's called a leaving group because it leaves. All right, so this is the second way. And that's what we're doing. This is attacking a carbon and kicking off a leaving group. We're applying a general mechanistic principle or step. Okay. Now when we attack a carbon or really any atom and kick off a leaving group, this is called backside attack. Because, as explained on that other page, the nucleophile comes in opposite the leaving group. So the leaving group is up, so the nucleophile comes in down. That's called backside. Okay? So that's very important. This will influence the stereochemical outcome. Now, at this point, why do we attack on the left? This chlorine is pulling here, but it's also pulling here. Why not? Okay? So there's actually partial plus both. But there's more partial plus here. Now this is showing the two different scenarios. If the chlorine pulls here, this is like it's showing the electrons being pulled towards the chlorine. So the bond is weakening and it's sort of becoming more of a lone pair. Because if it pulled it completely, this would just disappear and it would become a lone pair, right? So this is sort of partial. And as it's pulling, this becomes partial plus. We can also pull this way, which is more likely. Turns out this is more likely. Why? Because the difference is here. This carbon can take on more plus. Why can it take on more plus? Because it has rich friends. It has rich friends. Now, you could make an argument, I'm not going to open up a can of worms here, but if you have some argument you want to make here, please do. It has more rich friends, so it was able to become more partial plus. And so this is the more major sort of structural effect here. So there's actually more partial plus there. So when this guy has a choice, okay, it's like, here I come, which one am I going to go for? Woo! I'm going to go over here. Greater, what do you call it? I don't use this term much. What do you call charge attraction in physics? You call it, there's a word. Plus it's like minuses. Somebody's name. You got more of that type of attraction and it comes in, but it has to kick something off to bond. So it kicks that off. That leads to that product by backside attack. Okay. These reactions, if you look under B, what does B say? What does B say? Like electrophilic conditions without without a carbocation intermediate. So why am I showing a carbocation intermediate? All right. That's because this is not actually formed. NAF. You're not going to see that in your textbook. That's my terminology. Not actually formed. There is no carbocation intermediate here. Thus, if this is not actually formed, how many intermediates in this reaction?
One.
There's only one. It's called the chloronium ion. Did I show any other? I showed two, but I'm telling you one is not really there. So that means there's only one intermediate. So what's going on here, and why do I even show it? Okay, first off, what's going on is 1 and 2 are concerted. I hate to call it reactions because it's really, it makes it sound like it's two different reactions. We can maybe call it steps, but that still makes it sound like it's two steps. Steps 1 and 2 are concerted. What does concerted mean? They happen at the same time. Okay? These happen at the same exact time. And thus, this is really not there. The only reason I showed this is because it's in line with what we've been doing before. And so I think it just helps you guys see it better. If I just did all this arrow movement and showed this, I think you guys would just be, hold on, what happened here? So I do it stepwise, even though it's not. And this is not actually formed. This is just me on the board helping you see what's going on. It also allows us to see why that's not the mechanism attacking there. So concerted. Let's do a concerted. Here, I'm an alkene and you're chlorine. Okay? Now, if we do it single, high bond attacks chlorine. Oh, y'all bond. Y'all are chlorine. Okay. When I attack you, you got to pull your electrons away. Okay? Okay, so you became chloride, bonded to you. Here's the cation. Then we can say next step, now you have a lone pair, and you attack the cation. Back bond. Now we made the 3-membered ring, because then you came in and back bonded with your lone pair. Well, that's not 2 different steps. It all happens at the same time. So, as soon as I bond to you, we bond that way. Okay? We'll do it in bionic man formation. Okay? As soon as I bond to you, you bond to me. Bond. Boom. Chloronium. There was never a pairwise cation. It just, boom, everything happened at once. Boom, everything happened at once. That's what's really going on. I just show this to help us along the way. You can show this, but if you show it, you got to say NAF. Because if you don't say NAF, that means you must think it's really there. That's the way I do it. Okay, let's move ahead. Predict the products below. Right now, there's no stereochemistry. By the way, like I told you, all the reactions moving forward, we're going to have the same concepts. Back bonding. Backside attack. Products down here. There's no stereochemistry right now. Since there's no stereochemistry, this is the easiest reaction you'll do in chemistry, organic chemistry. Alkene, bromine. Add a bromine to each carbon, boom, you're done. Here we go. Boom, boom, boom. Bromine here, and a bromine there. Done. No, that's wrong. 1, 2, 3, 4. 1, 2, 3. How did I lose a carbon? That's because I did not pay attention close enough. I got to have a... Right? Common mistake. There you go. Bromine added to each carbon. That's it. Question?
Are they supposed to be anti?
Yes, but like I said, there's no stereochemistry here because to really be anti, you got to have 2 relative... No. What stereochemistry do you see here? The only thing you have here is right here, a chiral carbon. Now, as we go forward, you always get both. And it's going to be actually 2 structures. One where this bromine's forward and one where it's back. That's not chiral. So it don't matter how you draw that bromine. I could draw this with this bromine forward, and I could draw it with back. What do you call it when you draw both in a 50-50 mix? Racemic. We'll look at that a little bit later, but there's no trans or anti here because it's just not in here.
So we can just write racemic on our test, so we just write both of them? Or do you want us to draw them?
All of the above.
Okay, cool.
You know what racemic means?
Yeah.
If asked, could you draw them both on your exam? Okay. All of the above. We'll certainly hit that more. Okay, we also can use the so-called interhalogens. With interhalogens, we often see iodine. Okay, this guy has a permanent dipole. Which halogen is electrophilic? what is electrophilic? Which halogen of the two here is electrophilic? There's your dipole, right? Which one's electrophilic? The iodine, right? Do you know what electrophile means? If not, tonight's your time just to make sure you know what electrophiles are, right? Iodine. So the double bond attacks the iodine. You don't have to worry about, which one. Well, there it doesn't really matter because it's the same. But you got a permanent dipole. These electron attacks iodine, right? Kicks off the chlorine. You see, the chlorine wants this lone pair, that bonding pair. It wants it. It wants to pull it and take it on as a lone pair. So everything's getting what it wants. What does that give? Boom, boom, boom. Iodine here, plus here. Now, is this really formed? No. Because that plus Cl minus, right? What's going to attack this plus faster? The iodine that's right next door, or the Cl minus that's anywhere? Well, let me ask you this. You ever? Okay, let's clap some hands, right? Who's gonna clap my hand faster? Me with my other hand right here, or him? Let's raise. Who's gonna? Go ahead. You didn't even get out of your chair now. Why is this one faster? Oh, it's right here. It's connected. Boom. It's faster. That's much faster, yeah? Bam. What does that give? Boom, boom, boom. It gives this three-membered ring called an iodonium ion. That's a plus charge. That's really intermediate. This is NAF, right? Both of those arrows at the same time. And this is what books will show you. They'll do all this, and then they'll come in here with this arrow. And before you know it, it's just, I'm doing it separate. That's the way I do it. Here. Now the chlorine comes in. Which carbon is it going to attack? Because you're going to attack here and kick the iodine off of that, or here. It always attacks the more substituted. Here's your answer. It attacks the same as if it attacked here. But it just don't attack a free cation. It attacks that back bonded thing. It's already here. These electrons, bam, kick that off. And we're not really worried about much stereochemistry yet, but this tells us that the iodine is on the N carbon, the chlorine chlorine is there. Because we know mechanism. And we do not get chlorine here and iodine there. So this reaction does have regiochemistry possibilities. But do we get both regioisomers? No. You only get this regioisomer. So this reaction is regioselective. There's no regiochemistry up here because there's no choice. So, questions about that bottom reaction? Okay. How do we know this reaction does not involve a carbocation? Other than the fact that it makes sense that back bonding is going to be faster. Well, even though it's faster, we still don't know that maybe the cation formed and then the back bonding came in. Here's the main reason we know that this is a mechanism. It's because if you do this reaction, such as this, cyclohexene with chlorine, we can add a chlorine to each carbon, right? But it turns out we only get this outcome, trans. The two chlorines will be trans. We do not get cis. Why do we only get trans? Our mechanism needs to explain why only trans. Well, let's look at the mechanism below. We're going to leave cation on top or bottom. Same, it'll be equal. They'll both be secondary. Okay. I chose to leave it on top. It doesn't matter. Bottom would have been the same. If it had been a cation, this point, by the way, when the bond is made down here, this carbon is now tetrahedral. And so you have to show this either bold or dashed. I chose to show it bolded. Here, it can actually also be dashed. But at this point, if it was a free cation, chloride would attack it. But how does something attack a cation? Which side is it going to attack from? Both sides, right? We did this last time, piece of paper, both sides. Attack from both sides. So if this was the case, we should end up with this bolded, but these should be either way, front or back. But if this was the case, we would be getting some cis product. But I told you above, you don't get any cis product. So then this can't be the mechanism. By the way, if this bond had been dashed, and then this came in attacking cation front or back, because that's how you attack cations, front or back, you would have gotten dashed, but then you would have gotten front or back up here. And again, you would have gotten some cis. But we know that this thing, so this can't be the mechanism. Instead, what is the mechanism? I don't show it here. I'm going to have to show it here. This is not actually formed. Instead, what happens? This back bonds, right? And what does that lead to? First off, this is bolded. Okay, let's finish this up. This bonds, and it's going to be bolded. Because you're chlorine. There you go. You're forward. Now back bond. That bond's also going to be forward. It has to be. There's no way for that bond to be coming back. Okay? It has to be forward. So if this is up, the new one has to be also up. It can't be going projected back. There you go. That leads to this, back bonding. Then the chloride comes in. You can attack either one. But if it attacks up here, it's coming in and kicking this off. And when you come in and kick something off, how do you come in? Backside. Only. Opposite side. We said that earlier. It's also on the yellow page. We're not attacking a cation. When you come in and kick off a leaving group, it's always backside. That means if this bonds forward, this comes in from the back. And this leads to which product? Only trans, because this chlorine came in backside. Because it attacked the chloronium and not a free cation. So this makes more sense of why we only get trans. And this is the known mechanism and the most theoretically supported mechanism. Okay, we're out of time, guys. We'll finish this up. Look below, keep looking ahead.